This is a video for AQA Further Pure Mathematics, Algebra and Graphs, section 3.3, where we're considering the final conic section, the hyperbola, and what is called the rectangular hyperbola. Well, we know that the hyperbola is produced when the cut of the plane is at an angle which is steeper than the slope of the sides of the cone itself, so that it produces two branches. The hyperbola has a general equation: x squared over a squared minus y squared over b squared is equal to 1. Remember, the ellipse was x squared over a squared plus y squared over b squared equals 1. So this is our general hyperbola, and here's an example where we've got a value of a equal to 2 and b equal to 1, so that it's the equation x squared over 4 minus y squared over 1 is equal to 1. You can see those two branches clearly. Also notice that the point at which it crosses the x-axis is at plus or minus a. Now we can consider what happens for different values of a and b by looking at a GeoGebra file. So this shows the hyperbola we've just been considering with a equal to 2 and b equal to 1. So let's just first change the value of a and see what happens to those points where it's crossing the x-axis. You can see as we move, there's greater values, then it's becoming wider spaced apart. B, on the other hand, leaves the point where it's crossing the x-axis the same, but if you like, you could consider spreading out the line so that it has a greater gradient. Then you might be considering what is happening as x and y get very large. Well, the curve is in fact asymptotic to two asymptotes, and you can see there on this graph we've marked in the asymptotes, and this one is y equals 0.5x and y equals negative 0.5x. Again, I can change the values of a and b, so if I increase a, you can see that the values of the gradients is actually going down, and as I decrease a, the value of the gradient is increasing. On the other hand, if I increase b, the value increases, the gradient, and if I decrease it, the gradient is decreasing. So a is increasing the gradient, b is decreasing it as they both increase. At that point there, you'll see that the value of a and b are the same, and you'll notice that the asymptotes are at right angles to each other. We can consider, is that actually going to be the case every time we have a and b equal to each other? So let's just change a, let's make it 2 for example. There's a equal to 2. Now if we increase b, we know that's going to increase the gradient of the asymptotes, and when we get to b is equal to 2, you'll see again those asymptotes are at right angles to each other. So let's see if we can work out what the relationship is between the asymptotes and the values of a and b. Well, here's our general equation: x squared over a squared minus y squared over b squared is equal to 1. And we can consider that equation as x and y get larger, so approaching plus or minus infinity. And if that's the case, the 1 in the equation becomes insignificant, and we can say that x squared over a squared must be getting closer to y squared over b squared. Or in other words, y squared is approaching b squared over a squared. And therefore we have that the asymptotes y must be equal to plus or minus b over a. These are the asymptotes, and that explains then, doesn't it, that when we increase the value of b, the gradient of the asymptote that should be plus or minus b over a times x. Of course, that's just the gradient b over a. So as b increases, the gradient increases, and as a increases, the gradient actually goes down. So we've got our asymptotes at y equals plus or minus b over ax. And then of course we have that when a and b are equal, the asymptotes are at plus or minus x and therefore at right angles to each other. So we can use these ideas then to sketch hyperbola with certain conditions. So as an example of that, let's consider the following, which is the hyperbola passes through 4, 0, so we know it's going to pass through this point, and has lines y equals plus or minus x as asymptotes. Well, we know if it passes through 4, 0, it must also pass through negative 4, 0. And we're given the asymptotes as plus or minus 1/2 x, so we can draw those in. Here's one of them dotted in, and coming down in the other direction, of course. And then the negative one with slope of negative 1/2, so going through negative 8 and 4, starting here, coming through the origin. And that gives us a good idea of our asymptotes, so that as a sketch we would want the hyperbola to be approaching those asymptotes, without the crazy little bump in it, and at this side coming round, and there we are. So that's a reasonable sketch of our hyperbola. But we also want to find its equation in the form x squared over a squared minus y squared over b squared is equal to 1. So if we've got asymptotes which are plus or minus 1/2 x, then that means that if we let a be equal to 2k, then b must be equal to some value k. So we can substitute those into our equation, which says that x squared over 4k squared minus y squared over k squared is equal to 1. But we know that when x is equal to 4, then we have y is equal to 0, so substituting that into the equation, x squared must be 16 over 4k squared is equal to 1, which gives k squared equal to 4, and therefore k is equal to plus or minus 2. But if k squared is equal to 4, then we have that x squared over 4k squared is x squared over 16, and minus y squared over k squared, so y squared over 4 must be equal to 1. So that's our equation for our hyperbola, and I've got that together with a rather neater sketch on the next slide, and there we are. Well, that concludes the section on the hyperbola itself, but I also want to consider something which is called the rectangular hyperbola. Now, rectangular hyperbola is when we have those asymptotes at right angles to each other, but we normally consider the rectangular hyperbola with asymptotes which are the axes. So here's an example. the rectangular hyperbola, which has got axes, x and y axes as the asymptotes. The equation of a rectangular hyperbola is xy is equal to c squared. So you can see then we've turned the hyperbola sort of through 90 degrees now. And this is the usual way of representing the rectangular hyperbola. This is an example that you already know. Xy is equal to 1 would be y is equal to 1 over x. So if we've got c squared is equal to 1, then you have xy is equal to 1, or y is equal to 1 over x, which is the familiar rectangular hyperbola that you've already met. Different values of c, then the rectangular hyperbola will be in different positions but look very much the same shape. And again, we can show that with the GeoGebra file. This is the rectangular hyperbola we've just been looking at with c equal to 2, so it's xy is equal to 4. If I now increase the value of c, you can see that the shape stays the same, but it's moving further away from the origin. The slope obviously changing, but the general shape is the same, and then moving back in we get closer and closer, and of course then if I come to the value of 1, there's our y equals 1 over x curve. Well, that concludes this video on the hyperbola and rectangular hyperbola. In the next video we'll be looking at transformations of conics.